Hi guys, welcome back. So now let's go and see how we can actually use MATLAB Coder to make the transfer functions and also to make the state space representations. Okay, and how can we use those MATLAB coders to simulate the response of the system for different inputs? Okay. So first of all, what I'm going to do is I'm going to go to the live script here and I'm going to generate a live script here. Okay. So this is very similar to M file, but in fact, it's a little bit fancier because it shows things a little bit nicer. Yeah. So let's say that I'm going to go to example 18 that we solved in the class. Okay. And I want to basically generate this transfer function, which is 4s over s squared plus 8s plus 10. Now, if you look at this transfer function, you see that I have a numerator and I have a denominator. Okay. And this is exactly what we are going to do. We are going to give the numerator and the denominator to a transfer function and generate that transfer function object. Okay. For giving the numerator and denominator, just like the Simulink block, okay, I'm just going to use the coefficients of these polynomials. For instance, in the numerator, you see that I have 4s. This was in fact 4s plus 0. Yes? So my coefficients in the numerator are 4 and 0. If you just put 4, it's going to be wrong. Okay, so you make sure that your numerator is 4 and 0. And also your denominator is s squared plus 8s plus 10. So your coefficients are 1, 8, and 10. Okay, so let's go to the MATLAB coder. And here in my live script, okay, I'm just gonna put this one as CLC again, clear all, okay, and I'll close all the input, all the open plots as well. Yes, so at this point, I'm just going to define my numerator as, if you guys remember, it was 4 and 0. Yes. So this is just an array. Yeah. And my denominator is, in fact, 1, 8, and 10. So this is going to be 1, 8, and 10. Yes. So very easily. Yeah. Now, for making that object or the system, okay, I'm just going to call it a system, and I'm just going to make the transfer function. So my TF transfer function would be my numerator and my denominator. Okay. And if you run this code, go to here, okay, and run this code, you see that my transfer function is in fact 4s plus s squared plus 8s plus 10, which is exactly what I had. Okay, and this is a continuous time transfer function, and this is exactly what we wanted to have. Okay, now with this object system, I can do simulations. Okay, so MATLAB has some functions for some specific inputs. For instance, impulse and step are those two functions. Okay, and let's say that you want to find the response of the system for 10 seconds. So let's say that your time is 10 seconds. Okay, and it starts from 0, and you're going to have the time step as 0.01. Okay, and this is going to be 10 seconds. Yes, and you want to see basically how your system actually is going to react to impulse and step. Okay, so I would call it as y impulse first. Okay, and basically time, okay, as as impulse. Okay, and this is gonna just give you the system here, so your system that you defined. Okay, and if you do not put anything here, okay, it's gonna pick the time steps for by themselves. Okay, so I'm just gonna force this to use the time that I have. Yes, so it's gonna be using t with the sample time or the step time of 0.01 seconds. Okay, now when you run this code, um, this is gonna give you two arrays. The first array is y impulse, or the output of impulse, and the second array is y time. Okay, and if I minimize this, you see that I have an object here, okay, which is my system, numerator, denominator, this is my t, okay, and this is my y impulse. Okay, and if you look at the y impulse, you see that y impulse is exactly 1,000 by 1 or 1,001 by 1 array. Yes. Okay, so let's go back to the code and see how this y impulse look like. Okay, so I'm going to go ahead and plot this. Okay, so I'm going to say that plot time and y response, okay, or y impulse, sorry. Okay, and so for this system, I'm just going to plot them. Okay, and let's say that my x label, okay, is time in seconds. Okay, and my y label is the output of the system, yes, which is the y. So this is the output. Okay, and let's go ahead and run this. Okay, you see that when I run this, I have the output of the system with respect to time here. Yes, so at time 0, you see that you have the step impulse function, which is going to be a high magnitude applied at a very short time. Okay, and eventually your system is going to damp out because your input is gone. Okay, now let's go ahead and do similar thing with the input step. Okay, so for now, let's go ahead and copy all these guys, okay, and paste it here. Okay, and instead of impulse, I'm just going to use the step function here. Okay, so I'll call this output as y step, time is time again. Okay, and this is going to be step function. Okay, and this is going to be your step function. Again, I'm going to force the system to use the time array that I have. Okay, and at this point, I'm just going to plot another figure. If you do not use a figure here, it's going to overwrite the figure that you had. Okay, so I'm going to just use figure. So I'll basically have two figures right now, and I'm going to change this one as step. Okay, now y step is here, y step is here, time is here, time is here. Okay, so I'm going to run this one again. Okay, you see that I have two plots right now. The first plot is the plot of my impulse. Okay, and this is my step function. Okay, which you see that my step function also gives me a response that goes up, okay, and then goes to 0 again. Okay, now if you look at these two plots, okay, you can put the title for each plot. Okay, so for instance, I can say that title of the first plot to be impulse response. Okay, and title of the second plot to be step response. Okay, and if you run again this this code, you see that right now the title of the first one is going to be the step response. The title of the second one is the step response, sorry. The title of the first one is the impulse response, and you see that I have the output versus the input. If you want to add grid to these tables, okay, or to these graphs, okay, you just go ahead and say that, okay, I need a grid here, and I would make the grid on. Okay, and also I'll make the grid on here as well. So grid on as well here. Okay, and if you run it again, okay, you see that right now you have nice grids here. You can control how fine these grids or coarse these grids are. Okay, for now, if you want to learn more about these guys, okay, I'll refer you guys to the MATLAB website. And also, if you, for instance, want to learn something about step function, okay, you can just type here in the command window as help step. Okay, and with enter, it's going to give you some information about that function, okay, and how you can use it. For instance, you can just use a system that you generated with the step function, or the way that we did it, we forced it to use our own time steps. Okay, and also some other options that you can add to this step function. Similarly for impulse, for plot, the same thing. For instance, if you go ahead and say help plot, okay, and it's going to give you a lot of good examples and got a lot of good options that you can customize your plots in MATLAB. Okay, now let's go back to the code, okay, that we had before. Okay, right now you know how to generate a transfer function. You know how to get a response for a step and impulse function from that impulse inputs from that transfer function. Yes. Now what we're gonna do here is we're gonna see how we can actually give a custom input to our transfer function. Yes, to our system. So for this guy, what I have in mind is a sinusoidal function. Okay, so let's say that I'm gonna take the sine of my time here. Yes, so let's say that my new input is in fact sine of my time array. Yes, and what right now what I'm gonna do is I'm gonna just give it as a name as y sine. Okay, and time is gonna be a new function which is LSIM. Okay, LSIM. And with this LSIM, I'm just gonna pass the system to this guy. Okay, and then my input and then the time array. Okay, and just like the previous ones, I'm gonna plot the response. Okay, so when I run this, it's gonna give me y sine. Okay, and this is just an arbitrary input. It can be any function that you want. Okay, it can be cosine, it can be tangent, or it can be a combination of steps. Okay, that you have. Okay, any function. Okay, so copying and pasting the figure files. Okay, just make another figure. So instead of y time, sorry, y step, I'm going to use y sine here. Okay, and this is going to be arbitrary output. Okay, or arbitrary response. Okay, now let's go ahead and run this. Okay, and you see that it's gonna solve the problem for us. Oh, sorry, I forgot to put the semicolon here. So if you do not put the semicolon here, it's gonna give you a lot of things here. Okay, so this is the response of my system. Okay, so let me run it again, just get rid of those semicolon things. Okay, and you see that this is the response of the system with respect to my arbitrary input. Yeah, okay. So the next thing is how you can define your state space system. Yes. So for a state space, guys, what I'm going to do is let me just save this file, okay, as example, sorry, example 18 code, okay, code, and let's go ahead and make or generate a new file. Let's go with another live script. Okay, and I'm gonna start this one with CLC again, clear all. Okay, and then close all. Okay, now for this one specific one, what I'm going to do is I'm gonna solve example 11 that we had in the class. Okay, so look at example 11. Okay, in this example, you linearize, if you guys remember, you linearize a nonlinear dynamics. Okay, and also what happened here is you got your A and B matrices. Okay, and these A and B matrices are gonna be multiplied by delta X and delta U to give you delta X dot. Okay, and let's say that your Y is C delta X plus D delta U. Okay, so if you remember, your delta X was X minus X nominal. Okay, so I would say that my Y value is delta X. Okay, which is in fact you can get it by identity matrix multiplied by delta X plus a zero vector, which is 3 by 1 multiplied by delta U. Okay, so Let's go to your MATLAB. Okay, and at this point, what I'm going to do is I'm gonna generate the state space object here. Okay, to generate the state space object, excuse me, to generate the state space object, what you need to do is you need to define your A, B, C, D matrices. Okay, so look, A and B are directly given to you. Yes, so A and B, you can just copy and paste them from the notes. A, B is in fact 0, 0, 2, and A is this vector here, this matrix here. Sorry, this matrix, the one that you evaluated with the numbers. Okay, so here's the question: how can you make these matrices? Okay, for instance, it's a 3 by 1. How can you make these matrices? Let's go and see how we can do this. Okay, so the elements in one line, they're separated by a comma or a space bar. Okay, so in the first line you had 0, comma, 1, comma, and then 0. Yes, you want to go to the next line. Okay, just semicolon and enter, or just enter, doesn't matter. Okay, just enter. I always use semicolon and enter because it helps me to find things better. Okay, then the next line was negative 0.4. Okay, and then comma again, negative 0.2289. Okay, and then comma, and then 0.2. Okay, semicolon, enter, next line. Okay, so this is 1.5 and 0 and negative 1.14. Good. At the end, I'm just gonna press semicolon because I do not want to see anything in my command window. Yeah. Similarly, B was a column vector. It was 0, 0, and then 2. Yeah. And for me, I wanted to have the output of the system as delta x1, delta x2, delta x3. So I can get the output as cx plus du. And if I want to just see the delta x's, it sounds like my C should be the identity matrix and my D would be a 0 vector. So my C would be I, which is the identity vector, okay, matrix, sorry, 3, 3, okay, which is going to give me an identity vector. So let me just run this for you guys to see. Okay, you see that my C is right now identity vector matrix, which is 3 by 3. Yes. I could easily go ahead and type these guys out, but I do not need to do that. I am going to use the built-in MATLAB functions. Okay. And also my D for just giving the outputs as delta x, delta x1, delta x2, delta x3, it's going to be zeros of 3 and 1. Okay. And if you run this, you see that your D is a 3 by 1 vector, which is all zeros. Okay. This is going to be multiplied by you. Okay, so let me just put the semicolon here and there. Okay, and now navigate to the next part, which is making my state space object. Okay, for making that state space object, I'm going to just call it a system again. Okay, and for this one, I'm going to use, instead of the transfer function, which was TF, I'm going to use SS. Yes. For the SS, you see that it has given you some hints what you need here. Okay, so I would need A, B, C, D matrices for sure, and these ones are optional. You see that they are not highlighted. Yes, so I'm going to put my A matrix, my B matrix, my C matrix, and my D matrix. Okay, and if you run this, you see that it's going to give you your A in a vector format or a matrix format, your B, okay, your C, and then your D. Okay, and it's giving you that, okay, this X, A is multiplied by X's, B is multiplied by U's, and then so on and so forth. Okay. Now let's say that I wanna find the response of this state space object to a step input. Super easily, yes. Just make your time array. So my time is again from 0 with the time steps of 0.1 to 10 seconds. Okay. And I'm just going to get the response of the system as Y step. Okay. And time So basically, void step and time, okay, equals to step my state space object, which is system, okay, and now time, okay. And if you run this, it's going to give you the outputs of y, okay. Note that right now you have three outputs, okay, and they're your delta x1, delta x2, and delta x3, okay. And if you run it, okay, just to make sure that we are not making any mistakes, you see that my outputs are 1000 by 3. You see that? Okay. Now let's go to the code again, okay, and plot these outputs, okay. So I'm going to say that's figure, okay, and sorry, figure, and then plot my time, okay, and void step, okay, and void step. Now let's go ahead and make the labels again. X label is time in seconds, okay, and my Y label is basically the outputs. Yes, okay. Now you can generate, just put the title for this one, okay, and the title would be state space response, okay, to a step input, okay, and also you can just add the grids on, okay. Okay, now look at this. Let's go ahead and run this one again. Okay, you see that the output of the system y1, y2, y3 are given to you with the value of the step function. Okay, you can do very similar thing with the impulse function, or you can exactly the same idea using the LSIM to get any arbitrary output from your system. Okay, let me just save this file also as example, I think 11 of your course, okay. um, and I'm just going to save it, okay. And just one other thing, that the last thing that I wanted to mention to you guys is that you can always also solve these things in Simulink. Okay, so for instance, if you go to Simulink, okay, and then you have it your as state space, okay, it's just like the transfer function. It's going to bring you a block here that you can call your A matrix here, since your A is right now in the workspace. Your sorry, so your A matrix here, your B matrix here is in the workspace. Okay, your C matrix here, and then the D, which was a vector of zeros. Yes. Okay. And if you give any input to the system, okay, let's say that you're going to give the step input to the system, it's going to generate the outputs for you. So let's say that you want to see the outputs here. It's going to generate the outputs for you as well. Okay. And if you run this model, okay, you see that it's going to give you, it should give you very similar plots that you had before. Okay, in our MATLAB code, our step time was at 0. This one is at 1. Okay, so let's just make this one to step time at 0. Okay, and run this one again. Now these plots should be exactly similar to what you had here. Okay, it should be exactly similar to what you had here. Okay, so if there are a little bit of numerical inconsistencies, you can just go ahead and use or force the system to use the solver that you like. Okay, so for instance, I would go here and go to model setting, okay, and then force the system to use the exact model that I want. So this is about how you can actually use MATLAB Coder and MATLAB Simulink to solve these state space dynamics. If you remember, in our lecture, I told you guys that the hard part is getting the ABCD matrices. When you have them, you can dump them in MATLAB or Simulink, okay, and then it's going to take care of everything for you, okay. And the beauty of the Simulink is you can generate any function. Okay, also in MATLAB you can also generate any function as the input. Okay, but Simulink is a little bit more graphical. It's a little bit easier. So one last thing that I wanted to mention is how you can navigate from transfer functions to a state space and vice versa. So the functions that you can use are state space to transfer function, okay, or transfer function to a state space. Okay, so for instance, let's say that I want to go from transfer function state space to transfer function. Okay, so I would say that my numerator 2 and my denominator 2, okay, are gonna be state space to transfer function, and the arguments of this function, this is a built-in function in MATLAB, or you see that are A, B, C, D matrices that you have here. So A, B, C, and D. Okay, and also you can do very similar thing with the transfer function to a state space. Okay, so for instance, if you want to know your A, B, let's say A1 or A2, B2, C2, and D2 of the system that you had here. Okay, let's say that I'm going to use the previous code because this one was the one that we used for numerator and denominators. Okay, so let us halt on the transfer function to its state space. Okay, and I'll go back to the previous code. For now, let's say that how I can go from state space to the transfer function. So if you run this code, okay, you see that your numerator right now is a 3 by 3 matrix, and your denominator is a 1 by 4. Okay, so in fact, this is a third order system. So your denominator should be a third order, which is exactly what you have. So this is s cubed, s squared, s, and then the scalar. And since you have 3 outputs, for each of those outputs, you will have one transfer function. So the first line is the numerator of the first transfer function, which connects the input to the output as delta x1. The second one connects the input to the output as delta x2. Okay, and similarly, the last one is the one that connects the input to the output as delta x3. Okay. Similarly, if you want to go from transfer function to a state space, okay, let's say that in the previous example, you had the transfer function with the numerator and denominator. Let's say that you want to find the state space dynamics of this guy. So this is going to be A, B, C, and D, okay, equals to state space to, transfer function to state space. Okay, now if you do this, it's going to ask you to give you the values for the numerator and the denominator. Yes, so I'm just going to give you the num and then. Okay, and if you run this, okay, if you run this, you see that the values for A, B, and C, and D are given to you here in this problem. Okay, which you can verify this if that's correct or no. For instance, the denominator is s squared plus 8s plus 10. Yes, and let's see that if you can get exact the same results, okay, from this transfer function to the state space or no. Okay, so you first need to bring this one back to the input-output relationship, okay, and then from input-output relationship to a state space. For the previous example, which we went from state space to transfer function, this is in fact the formula that we had to go from the state space to transfer function, which was C Si minus A inverse multiplied by B plus D. Okay. So let me wrap up what we had so far. I showed you guys how you can use MATLAB Coder to generate a transfer function, to get the response of that transfer function or the system to impulse inputs, to a step input, and to any arbitrary input. Also, I showed you guys how you can change from or convert your transfer function to a state space dynamics. Similarly, I showed you guys how you can use MATLAB to solve um, SSR, okay, for different inputs. First, generate or establish your state space system. Then from that state space system, you can use with the exact the same method, step functions, impulse functions, or LSIM for arbitrary inputs. And also I showed you guys how you can actually use MATLAB coder to go from state space to transfer function.